Good day, class. Hope everybody's doing well. Today we're going to talk about resistors and capacitors. We're going to add the capacitors at the end of this experiment. We're going to look at them being in series and in parallel. So the purpose of me putting this handout up is just to point out, in the event that you get an old version, that there might be a few little flaws in here. Um, on your version within the system. It may be my courses, it may be Canvas. This little bracket is not showing up. So I just wanted to point that out to you. It shows up on table 1 and table 2. So just know that because it comes out as sort of an upside down question mark. So just know that that's just a closed off bracket, and the units there are in the bracket. So that would be kilo ohms. So that's primarily the reason I, I, I brought this one up. So we got a couple things that we're going to talk about here today. Capacitors, as I said, resistors in series and parallel. Um, we won't specifically define this, but it just basically we're just going to separate the voltage. I'll explain that in just a second. Likewise here when we figure out the voltage. We're going to be going to a simulation at the FET website, and let's take a look. So the first thing we need to know is we need to know how to define a circuit where the component is in parallel or in series. So the way you define that is, let's just say that we have a circuit component here. So in this case, we're going to have a battery, and we're going to attach it to 2 resistors. So this is the schematic in case you've forgotten or you hadn't got to it in your lecture class for these components. And you'll see them, when we go to the schematic on the simulation, you'll see them in 2 forms. You'll see a specific battery, and then the resistors you'll see as they are in the lab. And so let's just say we have a voltage source here of 10 volts, and we have these 2 resistors of, let's make them 3 ohms and 5 ohms. So when we get a situation like this, we may be interested in figuring out how much current flow there is going through here. So that might be our unknown. So our current is going to flow through here, around, and back. And there's also something called a voltage drop. And when we talk about the voltage divider in just a second, you'll see how that all plays out. So 2 things to note. So the first thing to note, we've come across this already, is Ohm's law. So Ohm's law says that the product of the current times the resistance is equal to the voltage. So that'll be one component that we look at. And then for us, for a circuit where our series are in, our resistors are in series, and I'll define that in just a second. We'll simply sum the resistances. So let's define R1 and R2. Let's say this is R1 and this one is R2. Now our end goal here is to create sort of a big, huge resistor, which we'll call R equivalent. And so we may have to go through multiple steps when the problem gets a little bit more complex. But this one is pretty straightforward. Now let's define what it means for a system to be the circuit to be in series. In a situation like this, if you look at the red line, you'll see our current flow. And where current flow has no only one path to follow. So for example, from here through this resistor into the second resistor, we can define this area as in series. So these two resistors are in series. So simply put, we're just going to add the two resistances. So the 3 ohm resistor, we'll leave off the unit for right now, plus the 5 ohm resistor gives us sort of a super resistor of 8 ohms. So this will be 8 ohms. The voltage, the voltage is still the same. And so what we might be interested in, as I said before, is what the current is going through this system. And so let's see. So if I modify this equation, I can say that I is equal to the voltage divided by the resistance, or 10 divided by that equivalent resistance. Let's put EQ here, um, divided by 8. And so 10 divided by 8 going to be 2 and some change. The 2 divided by 8, sorry, 1 and some change. And so we'll get 1.25 amps. So we know that that's going to be the amperage going through here. And so that's going to be helpful to us. So let's kind of redraw this again. We start off here at 10 volts. We know that there's a current going around now, and amperage is 1.25 amps. It's going to flow all the way through this circuit. And so what's interesting is the voltage drop. There's going to be a voltage drop across each of these resistors. And that's going to be important to hold on to, because we're going to use that in the next set of problems when we talk about something called Kirchhoff's law. And so remember, in conventional settings for a conventional circuit, we assume that our current flows from negative to positive, right? And in reality, electrons actually flow the opposite direction, but we've already taken up the opinion that current flows from negative to positive. And so if we look at the voltage drop, we'll call this V1. I'll just put just V1. And remember what our current is, 1.25, and we multiply by that resistance of 3, you can see that there's a 3.75 voltage drop across this circuit. And then over here, if we do the same thing, V2, same current, multiplied by that resistance, we come up with, this is 6.25 volts. And you can see here that we gain 10 volts here, and then we lose 3.75 volts at this point, and then the remaining 6.25 until we come back. So this current forms this loop or this circuit, and once we get back to this negative pole, we get down to a voltage of 0. So we get an increase, we get a drop across the resistor, so on and so forth. Okay, so that's a resistor in series. So one way to think about this is that the current has no options in which way to go. Right? So now we look at a circuit that is in parallel. So take a look at this one. So resistors parallel. And this time, let me give you the formula first. So we have 1 over R equivalent. Remember, that's what we're going to try and find, is going to be equal to 1 over resistor 1 plus 1 over resistor 2 plus so on. So the first time around, we'll just look at something really basic. We'll only look at 2 resistors that are in parallel. And so let's look at something maybe that looks like this. You can see here, well, let me finish drawing. You can see at this point here, we have current flowing. I'll draw it in orange this time. Current flowing will come through this wire, and this time it has an option in which way it could flow. And so let's call this R1, and let's give it a value of 10 ohms. And let's call this R2, and let's give this a value of 25 ohms. And we'll keep the voltage as 10 volts. Might make the math somewhat easier. Okay, so in this case, again, we're going to get these two resistors are in parallel. And so let's see if we can do the math on this one. So our R equivalent, 1 over R equivalent, is going to be equal to 1 over 10 plus 1 over 25. So I'll need to find a common denominator. The lowest common denominator looks to be 100. So the first one, I'll multiply top and bottom by 10. The second one by 4. And so I come up with 14 over 100. So our equivalent just means that you flip that and you flip the answer. Don't flip this part right here initially. You have to do the math on each one of those. And you'll see some, you may see some more complex equations that are on the, you might see some on the web. And my suggestion is just to make sure you can add those fractions in a simplistic manner. So in this case, our equivalent is going to be, just flip that over, 10 over 14. And if we do the math, we'll get 7 and some change. So 100 divided by 14 gives me 7.14. So this is about 7.14 ohms. So what this means is you would just take this, and our new equivalent system would look like this. We have 10 volts here. We have a new equivalent resistor that is of about 7.14 ohms. And then most of the time we'll be left with figuring out what the current is. And same thing, we use Ohm's law. So the current, one more time, would be equal to, that would be, let's see, if V is equal to I over R, I always have to kind of write that down, make sure I write this properly. We get a current, if we solve for I, we would get that I is equal to the voltage, 10, divided by the resistance, the equivalent resistance, which is 7.14. So 10 divided by that 7.14 is about 1.4 amps. It's actually exactly according to my calculator because I saved the entire answer. So the current that's going through here is 1.4 amps. And we can go through the same process again, and we would see, actually, in this case, the voltage drop across this component here would be 10 and 10 in both cases, right? So let's just verify that. So if we looked at the voltage drop across this area, and we would look at um, just this piece right here, we would say that, so what we'll see is through this area here, we'll see that the current is going to be 1.4 amps. But when we get to an area where the current has an option of which direction, the current is going to change in each one as it flows through each one of these branches. And so we could figure out in each one of the branches what its current would be. So the current in this area here, let's say I2, would be equal to the voltage drop. Now the voltage drop across here is going to be the same as over here, so it'd be 10 divided by the resistance. So in this area here, we'd get something about, let's see, 4 over 100, 40 over 100. C divided by 25. And so this would be about 0.4 amps flowing through this branch. And then out this side over here, the current, we'll say I1, would be equal to, again, that voltage, which is 10, divided by the resistance, which is also 10. And so we would get a current of 1 amp. Right? So we get the sum of these two adding up to be what that current is. And we'll see this in just a second when we look at our simulator. Okay, the next piece we want to look at, it might look a little bit more complex, but it's really not. And what you're going to need to do is you're going to just kind of need to break this up into separate pieces. My suggestion is to do the more complex piece first. So you would have these two resistors, and then now you would have a third resistor possibly in this setup. So I won't walk and go through this all. So you have a combination of resistors in parallel. These two are in parallel. And relative to this resistor, this semi, if you will, equivalent resistor is going to be in series with this resistor. So let's do this in pieces. I won't solve it per se. So what you're going to do is you're going to combine these two into its own equivalent resistor. So maybe we call that R equivalent 1. That comes by way of combining those two. And if this is R1 and maybe this is R2, so this is, let's see, I want to write this so that you don't get confused. So this is 1 over R1 plus 1 over R2 equal to 1 over R equivalent 1. And so this next piece down here, this next resistor would be R3. I'm just rewriting that down here. And so you just kind of continue this process. And so our next step here would be to add these two resistors. And so you would take whatever value you get here, and since they're in series, remember In this case, you can see that these two only have one direction to go. Your new circuit would look something like this, and maybe I call that R equivalent, and that would come by way of adding R equivalent 1 plus R3. And in that case, I'm just going to make up some numbers. Let's just say that this turned out to be equal to 10, and this turned out to be equal to 25. Then R equivalent would be equal to 35. And then you would go from there. So my suggestion is to work with the most complex piece first. A couple more examples here, and then we'll go to the simulation. We're going to look at capacitors. And for capacitors, it's just the opposite. Okay, so if we have a battery that's going to provide power to these capacitors, and so you'll see here the capacitor symbol looks kind of like the battery symbol, so be careful in how you write these. Just these are called plates, and the plate is going to store a charge for us, just the way that we allow current or energy to sit. And so again, maybe we have something of 3 volts over here. And now capacitors, their units are going to be in farads. So be careful when you write down your units, right? You don't want to use C, because C often corresponds to coulombs, and that corresponds to a charge, which we're going to also look at relative to these plates here. And so essentially what we're going to do is we're going to create, a charge where we get positive and negative charges on each one of these plates. And so let's just say at this um, first one has a charge of 2 farads. It's pretty large. And then the second one is of 3 farads. So again, as you kind of remember, to determine if they're in series or in parallel, you have to kind of look relative to one another. If the chart or the current has um, an option, and in this case, it doesn't have an option. So this is in series, but the way we quantify and we get our new, if you will, big equivalent capacitor is we look at the equation that looks like this. So 1 over equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus dot, dot, dot. So in this case, we'll draw the new, if you will, supercapacitor. Got a 3 volt over here, and we're going to try and figure out what C equivalent is. So the math is just like you just did for resistors in parallel, except now we're dealing with capacitance. And so let's see, we got 1 over CEQ. Do the math on these. I'll show you a quick way of doing this in case you're a little rusty on uh, fractions. So you have 1 over 2 plus 1 over 3. So one quick way, in case you don't know what the lowest common denominator is to multiply in that direction. You get 2. 2 times 1. Multiply in the other direction. 3 times 1 is 3. You're going to add those together, and then you're going to multiply those two and get 6. So 1 over capacitance equivalent is equal to 5 over 6. And so our equivalent capacitance is going to be equal to 6 over 5. And that is about 1.2 farads. Okay, so this is 1.2 farads. And you'll see an equation where I ask you to figure out or look at the stored value in the charge. Actually, sorry, the charge. So this is the charge. This is in coulombs. So that's why I don't need you to use C for your capacitance abbreviation. And our um, our charge is equal to the amount of capacitance times the voltage. In this case, the equivalent capacitance is 1.2 farads, and the voltage is 3 volts. We have a farad volt, which is the same thing as a coulomb, so we'll get 3.6 coulombs. That's how much charge this plate has, and there's going to be that same charge on each one of those pieces as well. So let's go to the simulation. Okay, so we are now looking at a simulation where we're looking at two resistors in parallel. And so it's um, pretty easy to manipulate these components. Um, you'll just grab the wire and place it as necessary. If you need to cut out something, just double click it and click the X, or click the scissors. If you want to piece it back together, you can. And as I said before, we have a way. Initially, we thought everything was in a conventional sense, but we found later on that currents or electrons flow opposite of what you're seeing here. But we've adopted these values, and so we'll stick with that. So the conventional method is what is most often used. And so couple things that you're going to want to play around with here. You can click on the labels to see if you want. You don't necessarily have to have this. It's just a switch that controls the flow of current. You can see the current flow. You can also switch to the schematic view of this. If I take away the values, it'll look a little bit cleaner. Okay. And so typically I just leave it in the default setting where you can see the actual objects. So we got two resistors here. We have resistors in parallel. And if you see right here, you can see as this current flows through here, it has options in which way to go. And then, and so we can see that these two are in parallel to one another. So if you take this voltmeter and you put the black side on the negative side of a component and the red side on the positive side, you'll see the voltage drop. And here you can see that the voltage drop is 10 volts, which is the same as what the voltage drop would be across this battery. This is an increase, actually. This is a voltage increase. And likewise over here, you can see the negative, which is a voltage drop. If you happen to put them in the opposite direction, not a big deal. It'll just give you the opposite value. But you should realize that there's a voltage drop. Now, the other thing that you're going to want to play around with is the ammeter. And you can take this object here, you can just use the little spyglass and place it right on. Or you can take the ammeter component and grab it, but you have to place it in series with whatever component you're interested in. So I have to put the component in series with that resistor, so you can see what the current is through there. So it's just a little bit easier to use this, but in reality, and remember this one was 1.4. In various settings, you'll have to place the ammeter in series and the voltmeter, if you will, is in parallel with the component. All right, so that's a good one to know. Voltmeter is measured in parallel, right? Because the current is actually flowing through this piece here. and ammeter is in series. So let's just dump that back in here. Let's delete that, and let's put this back together. Let's place this back over here. Okay, so there's a setup where you have a component in parallel with one another. And then my second setup here, I use some resistors that are pretty high, have pretty high resistances just to switch it up a little bit. 1,000 ohms and 1,000 ohms. And since these are in series with one another, the total resistance would be that of a 2,000 ohm resistor. And so let's just build one real quick so we can put these wires together. We'll grab a real powerful resistor, something that holds a lot of resistance, has a lot of resistance to it. We can change the resistance all the way up to 2,000. And what I'm trying to do is I'm just trying to show you how the current compares. They should be the same as we build this. It doesn't have to be a nice, clean looking picture. Probably should, so you can see it a little bit better. Yeah, let's cut that out. Just kind of build it a little cleaner. So you can see here that there is a current flowing. It's just moving really slow. And let's put it in the conventional manner, the red arrows. And let's see where they go. About 9 volts. It's going very slowly. Just kind of hard to see. They're moving to the right here. And if we wanted to make sure, we just put our ammeter here. What's going on? So actually this number is pretty negligible. So that's why you're not getting a measurement here. So what we can do is we can lower the resistance. And we should see that there is current flow at some point here. I guess because, let's see, we can increase the voltage and we can see that there is a current flow. So I increased that to 56 volts. Let's change this back to 2,000 so we can get a comparison. And then I'll change this one to 56 volts as well. So again, we can get a comparison. So we got about 3/10, 3/100ths of an amp here. And we should see the same thing over here. So these two resistors give us the same current flow at any point along in this circuit series. Okay. All right. So you'll look at the simulation for capacitor later on. I didn't want this video to be longer than what it is. It's probably already 10 to 15 minutes long. So if you have any questions, feel free to give me a call or email me. All right, take care.